Now that's because all the operations are linear. So I can add two messages together over here. Each one of those messages produces its own code word, but when I add them, it also produces a code word, which is the sum of the original code word. Another consequence of this is that all 0 is a code word. So if my message vector is all 0 on the left, multiplying that by the generator matrix will produce the all 0 code word. So it doesn't matter what the generator matrix is, all 0 over here will always produce all 0 in the output. The nice thing about linear block codes is that it's very easy to tell what the minimum Hamming distance is. So the minimum Hamming distance, actually, let me start with some definitions. The Hamming weight W of a sequence is the number of non-zero positions. So for example, the Hamming weight of the sequence 0, 1, 1, 0, 1 is what? 3. So it's the number of non-zero positions, 1, 2, 3 non-zero positions. For a code, C, W min is the minimum Hamming weight defined as W min is equal to the minimum of all code words in the code. Again, I'll use script capital C for the code. I didn't use that over there, but let's start using that here. Minimum over all code words in the code of the Hamming weight of that code word. So what's interesting about linear block codes is that for any linear block code, minimum Hamming distance d bin is equal to the minimum Hamming weight of any code word.
Question?
Yes?
So the Hamming weight is the number of non-zero positions.
Yes.
But since linear block codes always have the 0 code word.
Good point. The minimum Hamming weight is defined as this for C is not equal to the 0 code word. That's a good point. So, why is this? Well, what's d min? D min is equal to the min over all C1 and C2 in the code of the Hamming distance between C1 and C2. Now, there's another thing I should point out over here. This is actually quite important. The number of positions actually, let me back up. The Hamming distance between two binary sequences, DAB, is equal to the Hamming weight. If these are both binary sequences, that's equal to the Hamming weight of A plus B. Why is that true? So that's true because if let's let A equal the A1, A2, so on up to AN. And let's let B equal B1, B2, so on up to Bn. So if AI equals BI, then AI plus BI mod 2 is equal to what? AI plus BI mod 2 is 0. That's because if AI equals BI, there's only two possibilities, 0 or 1. 0 plus 0 is 0, and 1 plus 1 is 2, mod 2 is 0. And if AI is not equal to BI, AI plus BI is equal to what? It's equal to 1, because there's again only two possibilities, 0, 1, which is 1, or 1, 0, which is 1. So weight of A plus B is equal to the weight of A1 plus B1, A2 plus B2, and so on up to AN plus BN. And AI plus BI is non-zero only where AI is not equal to BI. So therefore, in all the positions that are different, A plus B is equal to 1. So therefore, the distance between A and B is the Hamming weight of A plus B. Okay, so if that's true, let's look back here. This is equal to the minimum over all C1 and C2 in the code of the Hamming weight of C1 plus C2. But C1 plus C2 is a code word in the code. And let's just call this C prime. And C prime is itself in the code. So this is equal to the minimum over all C prime in the code of the Hamming weight of C prime, which is equal to the minimum Hamming weight of the code. So that's important for the following reason. If a code has n code words, in order to calculate the minimum Hamming distance, we have to compare each pair of code words, and there's on the order of n squared of those. However, if we have a linear block code, in order to get the minimum Hamming weight, we just need to look at each individual code word in isolation. So for general code, we have a problem of n squared. For a linear block code, we have a problem of n. So it's much more efficient to figure out the minimum Hamming distance. So let's have a quick example. Let's let G be equal to this. So, my message, in order to multiply mg to get a code word, I multiply m1, m2 by 101, 011 to get, and to make the dimensions work out, I'm multiplying this row vector by these three positions, so I end up with 3 bits in the code word. So just as an aside, this code is k rows, n columns.